So today we're going to be starting chapter 6, which covers trigonometric identities. Uh, this is going to cover something a lot different than anything we've actually dealt with before. Trigonometric identities are going to build slightly off of the things we've already learned. There will be a few applications to things like special triangles and stuff that we've learned before that we can actually apply to this new unit. But for the most part, this unit's going to be a lot of new information. So in other words, reach out to me if you're ever having trouble with it. Today, we are going to cover what are identities. That is part of the name of this unit, trigonometric identities. We're going to talk about what that is and how they're different from equations, because they are quite similar to that. We're also going to talk about what it means to prove an identity, but I want to let you know right now that's not the focus for today. It's just good to know for tomorrow. Ultimately, we want to be proving trigonometric identities. We're going to have to know what that means today, but we won't worry about it until tomorrow. There's three different types of identities that we're going to learn today: reciprocal identities, quotient identities, and Pythagorean identities, also called Pythagorean, if you want to pronounce it that way, identities. You don't need to know that they're all different, really. I would actually suggest you don't group them into different things, but we'll get to it when we get to it. So, equations and identities. An example of an equation would be 3x squared plus 3 equals x squared plus 11. That's nothing new. We've seen equations like that many times. You've seen that since like early middle school, right? But an example of an identity would be x plus 1 squared equals x squared plus 2x plus 1. Now, to the untrained eye, these look like kind of like the same thing, right? They look like, oh, they're both equations because there's an equal sign, but they're not. This is an identity, and this is an equation. What do you think the difference is between an equation and an identity? It's not immediately obvious. I want you to think about both sides of the equation and what they're equal to, and I'll let you know right now. So an equation is only true for certain values of x. It could be one value, it could be two values, three values, who knows, but it's not true for every value of x. And we can confirm that it's an equation simply by solving it. Solving it, of course, usually has meant get the x all by itself and figure out what it could be equal to. So to do this, what values of x make this equation true? Again, like I said, we want to get x all by itself. So how about we move this x squared to the left-hand side? That would make it 2x squared plus 3 equals 11. And then we can minus 3 on both sides to get 2x squared equals 8. Then divide by 2, and we have x squared equals 4. And of course, to finish this off, we just have to square root both sides. But remember, when you square root a number, it can be positive or negative. So we'd say x equals 2, but x could also equal negative 2, because if it was negative 2 squared, that's also equal to 4. So there are two solutions here, and those are the only values of x that would make that true. If you tried plugging in x as 0 here, for instance, you're going to see 0 plus 3 is 3, 0 plus 11 is 11, 3 equals 11. I don't think so, right? So in other words, an equation only works for certain values of x. An identity, as you may have already guessed, is true for all values of x. No matter what you plug into it, it's going to be true on both sides of that identity. Now, we can confirm that a statement is an identity using a concept called mathematical proofs, which is what we're really going to get into tomorrow. But basically, the most simple definition of a mathematical proof is that it involves showing that the left side is identical, so totally the same thing, as the right side. As time goes on, we're going to go into this a little bit more in detail, of course. The whole idea of an identity is you can't make the assumption that these sides are equal until you've actually shown that both sides are the same thing. So in other words, you have to just work on one side of the identity and work on the other side of the identity. Sometimes you only have to work on one side or the other. You don't have to work on both, but you're not allowed to cross that equal sign until you've actually proven that they're the same thing. So again, it's kind of like Clark Kent and Superman. They are different identities. Here's a real example, right? They're different identities, but in order to prove that, you'd have to show that this side is the same thing as this side without actually making a cross the equal sign assumption, right? Now, prove this identity. Again, we're not getting into proofs today, but I'll just show you what a proof could look like. We want to show that x plus 1 squared is an identity, so it's totally equal to x squared plus 2x plus 1 for all values of x. Again, to do this, we want to show the left side is identical to the right side. Work on one side or the other. I think I'll work on the left side. X plus 1 squared could be expanded out. Let's just go LS for left side. X plus 1 could be expanded out. X plus 1 times x plus 1. Then you could use your FOIL, so first outside, inside, last, to expand this out. That would become x times x is x squared. X times 1 is just x. 1 times x is another x. 1 times 1 is 1. That, of course, simplifies to x squared plus 2x plus 1. And what do you know? the left side and the right side are equal to the same thing. So we could say LS equals RS. We've just proved an identity. That was all there was to it. That, of course, is a very simple example, relatively speaking, but that's generally the idea of how we prove things. Okay, a lot of information on this, but it's not as much as it actually seems. Trigonometry, sorry, has a lot of identities, like an absolute metric ton. I'm sure you've looked at your formula sheet. On the entire right-hand side of your formula sheet, all of those, what you may have thought were equations, are, for the most part, identities. These are identities that we're going to be using for proving later on. There's a lot of them. Obviously, you don't have to memorize them. They're given to you on your formula sheet, but there's a ton of them, right? Now, these statements are true for all values of their variable or variables, right? These are already proven. We won't be asked to prove any of these. These are kind of just like your toolbox that you can pull from. These are the things that are given to you as facts. You don't have to prove them. Just so you know, this letter here, of course, is theta. We're familiar with that. It shows up in identities that only have one angle. So like this one right here only has theta in it because there's only one angle. These angles are the same thing, right? So maybe sine squared of 50 plus cos squared of 50, that's always going to equal 1. We'll talk about that particular identity a little later today. For some of the ones that we're going to talk about in a couple days, because they're more advanced, are the ones that contain more than one variable. So this little symbol here kind of looks like a fish kind of thing or something. That's alpha. It's a Greek letter. And this one, which looks like a B that kind of has like a long like side to it, that's called beta, right? So alpha and beta. These show up in identities that have two different angles, where one angle is alpha and another angle is beta. They have to be different angles, right? So they're not the same value. Alpha and beta are not the same angles. Maybe alpha's 10 degrees and beta's 70 degrees or something like that. We'll look at these in a later lesson though. And of course, if you look at the formula sheet, there's a lot of them where they show up, like pretty much most of these down here. They do use, even for a single angle, these ones down here use alpha for some reason. I don't really understand why. They could have used theta on it. It's just the way your formula sheet was made. Anyway, again, as I mentioned, these identities are given to you. You won't be asked to prove them. They may be part of larger identities that you will be asked to prove. However, we'll get into that more tomorrow. And if you have an expression in a problem that contains one side of an identity, you can actually swap that side of an identity for the other side of the identity, which might make the problem easier to solve. So for instance, I'll just erase this just so we can see it a little better. If you had an identity, something equals something else, and one side of that identity, the left-hand side, said, let's just pick one here. How about this? What if it said 1 plus tan squared theta? And then it was equal to some other jumbled mess. Now, if it was equal to secant squared theta, you'd already be done. You'd be like, okay, yeah, we're done our proof. We already have that identity on our formula sheet. We're good. But what I'm saying here is if this was equal to some big other jumbled mess, you could see this and go, oh, that's on my formula sheet. I could actually change this just to secant squared theta. Maybe that'd be a little easier, right? That's a little bit reduced. Maybe that would be easier for you somehow, right? That's kind of the idea here. We can use these kind of as a replacement for what we already have. All right, I know I've rambled about that, but it was important to talk about it. So what we're getting into today are the reciprocal and quotient trigonometric identities. You don't have to worry about the names of them. You just have to know that they exist. All of these identities, these reciprocal and quotient ones, are ones we've actually seen before. This is nothing new to us. We've actually worked with these identities before, and you just didn't know that they were identities. So the reciprocal ones, or sorry, the quotient ones, I'll start with those first, are tan theta is equal to sine divided by cosine. That's what tan is. It's just sine over cos. And because tan has a reciprocal of cotangent, then you could just take the reciprocal of that and have it as cosine over sine. So those ones we call the quotient identities because, of course, they contain a quotient. Now, these ones down here, cosecant, secant, and cotangent, those are your reciprocal identities, right? So cosecant is the same thing as saying 1 over sine, and that is the truth no matter what the value of that angle is. So therefore, those are your identities. If you ever saw cosecant theta, you could replace it with 1 over sine theta or vice versa. That's why it's an identity, and that's why it's useful to be used. So generally speaking, however, anything aside from sine and cosine are just considered difficult to work with. Even tan. We know tan is something familiar. You'll learn about it back in grade 10. But in terms of proving or simplifying identities, tan is actually considered a little challenging to work with. So anytime you see a tan, oftentimes, not all the time, but oftentimes, you're going to want to change it so it's sine over cos. Believe me, it'll actually make things easier. Not every time, of course. There are going to be some cases where it's not, but usually that is the case. The reciprocal identities, that should be no surprise to you. Those things just suck. And we've always said that. those identities are just ridiculous. Whenever you have them, please just change them into sine or cosine. There are some very rare exceptions where you don't have to, but just generally speaking, it's a good idea. Now, ideally here, we'd also like to simplify a complex expression containing many trig ratios down to a few trig ratios as possible by using these identities. So if you've got a whole jumbled mess that's all strung together, we want to try to trim it down so there's only a couple trig identities, or even better, only one trig identity. That's what we're really going to be focusing on today. Again, we're not going to prove that left-hand sides equal right-hand sides today. We're just going to work about simplifying things down. That's all. Okay, so for our first example here, express the following as a single trig ratio, it should say. Sorry, that's a typo. As a single trigonometric ratio. Secant theta times sine squared theta times cosecant theta. Well, remember some of the advice I gave you. We don't like anything except for sine and cosine. So wherever possible, try to get rid of anything that isn't a sine or a cosine. So we'll start with this secant theta. Remember, secant is the reciprocal of cosine. You don't have to remember that. It is on your formula sheet. But secant will therefore become 1 over cosine theta. And then sine squared theta, there's nothing wrong with that, so we'll leave that alone, sine squared theta. And then cosecant theta, well, that's the reciprocal of sine, so we'll make that 1 over sine theta. So I've got a bunch of fractions that are being multiplied together. The sine squared theta isn't a fraction, but you know what? Just to make things consistent, let's make it a fraction. We'll make it sine squared theta over 1. And then we'll multiply all these fractions together. And remember, to multiply fractions, you just multiply the tops and you multiply the bottoms. Well, 1 times sine squared times 1 is, of course, just sine squared. And on the bottom, we have cosine times 1 times sine. So that just gives us cosine theta times sine theta. So what's interesting here now is we have sine squared on the top and a sine on the bottom. Well, this sine can be crossed out and one of these sines can be crossed out. So this is just going to leave us with sine theta over cos theta. Hopefully that seems familiar to you. If it doesn't, please take a look at your formula sheet. That's actually one of our quotient identities. Remember, sine theta over cos theta, that's just tan theta. So right there, we were able to get that as a single trig ratio. This whole expression is the same thing as tan theta. If I had made this question a proof, I could have said, prove that secant theta sine squared theta, cosecant theta is equal to tan theta. And in order to prove that identity, you would have just had to work with this left-hand side and change it down using your identities to find that it was actually tan theta is equal to tan theta. And we would have proved it, right? So that's really all proving is. You just simplify one side or another side or both sides down until you get both sides to do the same thing. Not too bad. Moving on. Once again, same typo. You can tell I just like duplicated the slides each time. Express the following as a single trig ratio: sine x plus cotan x times cosecant x. Sorry, cos x. All right, so again, it's probably a good idea to get rid of anything that isn't a sine or a cosine. So these two guys are fine, but cotangent is going to cause us some problems. Now, you can think of cotan, of course, as 1 over tan, but that doesn't get rid of the problem that we have that it's still not a sine or a cosine. So remember, cotan could also be thought of as being cosine over sine. So let's get to it. Sine x plus cotangent, which could be written as cos x over sine x, times by cos x. Well, I guess the next thing we could do is we could combine this part into just one big fraction. So I could say that this is sine x plus cos x over sine x times cos x over 1 technically is going to be cosine squared x over sine x. And then I guess the next thing we would have to do, because this is kind of awkward having two different pieces in here and writing it as a single trig ratio is not going to be possible. I think we only have one choice here. We got to recognize that this is sine x over 1 plus cos squared x over sine x. In order to add fractions, they have to have the same denominator. This one doesn't have a denominator of sine x, but we can make it have a denominator of sine x by timesing both the top and the bottom by sine x. That's going to give us sine squared x over sine x plus cos squared x over sine x. And of course, since they have the same denominator, we can just add them together. This becomes sine squared x plus cos squared x over sine x. All right, so this is where things get really weird. If you have a look at your formula sheet right now, though, there's going to be a new identity that we haven't talked about that's actually going to help us out with this. If you look on your formula sheet, it's about, oh, I'd say about a quarter of the way down on the right-hand side. There's one that actually says, I'll just write it at the top, there's one that says sine squared x plus cos squared x is actually equal to 1. I kind of mentioned that earlier in this lesson, but you might not have picked up on it. What that means is, because this is on our formula sheet, we can accept that as a totally true fact. It's already been proven, it's given to us. So instead of saying sine squared x plus cos squared x, I could replace this with a 1. So I could say this is 1 over sine x. Well, we want to express this as a single trig ratio. You might think of this as a single trig ratio, but we can do better. We can actually write it not as a fraction of a trig ratio. We can understand that we're writing 1 over sine x, which is the reciprocal of sine. The reciprocal of sine is cosecant x. And that writes it as a single trig ratio. So again, when you are proving or simplifying a trig identity, it's often a good idea to get rid of anything that isn't a sine or cos, but you're more than welcome to have your final answer as something that isn't either sine or cos. As a matter of fact, that's pretty ideal actually sometimes. All right, moving on. Verifying identities. Sometimes you don't need to fully prove an identity. Sometimes you only care that it works for a certain case, like an equation would. This is called verifying. The bottom line is you just plug in whatever number it gives you to both sides of the equation or the identity, if it is, and just show that it's the same. This is kind of silly. I'm just going to do one real quick example here. Verify that tan x equals sine x over cos x for x is equal to 30 degrees. We can verify this no problem. Like, you can literally throw this in your calculator if you want. You could use, well, since it's 30 degrees, you could use special triangles if you really want to go crazy. I'll go crazy here. We'll say that this is our special triangle, an awesome triangle I just drew. 30 degrees, 60 degrees, 90 degrees. I know it's been a while, but remember your hypotenuse is always 1. Opposite of 30, I've always remembered to be 1/2. And then opposite of the 60-degree angle, of course, is √3 over 2. It's that really weird side. Tan x, so x is 30 degrees. Tan of this is going to be opposite over adjacent. So for the left side, opposite over adjacent means we have 1 over 2 over √3 over 2. Well, 1 over 2 over √3 over 2 is a fraction divided by a fraction, so we'll keep, change, flip. Well, 2 and 2, those will cancel out. We're going to be left with 1 over √3. Cool. All right. Now for the right side, got to do kind of the same idea. Sine x, so sine of 30 is opposite over hypotenuse, which is going to be 1 over 2 over cosine x, which is adjacent over hypotenuse, which is √3 over 2. That's a 3. √3 over 2. Oh, and what do you know? It's exactly the same thing. It's 1 over √3. See, this is kind of pointless, right? I don't like verifying, but again, it's part of the curriculum, so there you go, done. All right, determine all of the non-permissible values, the NPVs. It's been a long time since we talked about that, in degrees for that identity. So sometimes it's important to recognize that even in identities, you have NPVs, things that you can't plug in. Well, remember, an NPV is basically just wherever you're dividing by 0. So what this is really saying is we're looking for where cosine x is equal to 0, because if cosine x was equal to 0, you'd be dividing by 0, and that's just, you know, a no-no. You can't be doing that, right? To solve for this, you can use inverse cos if you like on your calculator, but I'm not even going to use a calculator here because I don't have one handy at the moment. So I'm going to remember that the unit circle tells us that cosine is the value of our x, right? Cosine is our x, sine is our y. So we're looking for where cosine, or in other words, our x value on a unit circle, not to be confused with this x as an angle in here, but the x value on our unit circle is equal to 0. Well, that would be where x is 0 is 90 degrees and 270 degrees. Now, that is all of your non-permissible values for you know, a degree of 0 to 360 degrees, because again, we are working in degrees, but we want all of them. So this is where we have to use that really long general solution. What I would say is every coterminal angle to 90 degrees, so 90 degrees plus 360n, that's going to be a non-permissible value. And then same with 270. But the good news is these two values are actually pretty fortunate because they're only 180 degrees apart from each other. So in other words, if I took 90 degrees and added 180, I'd be down at 270. And if I added another 180, I'd be coterminal to 90 again. And then if I added another 180, I'd be coterminal to 270 again, and so on. Bottom line is x is going to not equal, x cannot equal 90 degrees plus or minus 180 degrees times n, where n is an element of the natural numbers. In other words, what this is saying is x can't be any x can't be 90 degrees plus or minus any multiple of 180. So whether you went 180 once or twice or 3 times or 4 times, whatever, as long as it's any natural number, that's what it can't be. That's kind of a weird thing. If you need any help with that, ooh, I totally butchered that. If you need any help with that, please let me know, but it's not the important thing from all of this. All right, the last thing we've got to talk about today are the Pythagorean or Pythagorean identities. There's 2 different ways of pronouncing it. They're both correct. We can generate this one ourselves, actually, believe it or not. I think this is a really good exercise. You could accept it off your formula sheet just as is, or we can actually figure out why it exists. Draw a unit circle and mark a point on that circle in quadrant 1. So I already threw a unit circle in here. So you know what, I'll just mark a point. How about I use this one? Doesn't matter. I can use literally any point. It doesn't have to be on the grid. Any point in quadrant 1. Connect with a line to the origin. Okay, there we go. And draw the angle theta. All right, so far so good. Then label the side lengths using only that angle theta. This is where it gets a little weird. We're not allowed to call the side length x and y. That becomes too easy. And remember, of course, we could say it's like that right there. But it would be too easy to call this x and call this y. What we do know about this triangle that forms is that our hypotenuse is 1, because it is a unit circle, so the radius of that circle, no matter where it's drawn, is going to be 1. In terms of this angle theta, I kind of mentioned it earlier. If we're interested in finding, let's say, this opposite side, we have the opposite side and the hypotenuse. Well, that's going to be sine. We could say that this side right here is sine theta. There you go, because sine theta is opposite over hypotenuse. Since you're just dividing by 1, you might as well say sine theta equals this. No big deal. Likewise, this other side right here is your adjacent side, so it's going to be cosine theta. Now, how does the Pythagorean theorem fit into this? Well, if you thought of your side lengths as being a squared plus b squared equals c squared, we could therefore say we have sine squared theta plus cos squared theta equals your hypotenuse, which is 1 squared. But 1 squared is kind of silly. 1 squared is just 1, so I'll just ignore it altogether. Well, hey, wait a minute. We used this. We used this like just a couple minutes ago. It was on our formula sheet. Well, that's why it's called a Pythagorean identity, right? Because we can establish it using Pythagoras' theorem. We just created this just out of thin air right now, and this is proven that sine squared theta plus cos squared theta is equal to 1. Huh, what do you know? So the primary one, again, as we just found, is sine squared theta plus cos squared theta equals 1, but there are a couple other Pythagorean identities here, and they're a little weird to generate. You don't have to know how to generate them, but it's just kind of good to know. You just have to know they exist. If you divided all of the terms in this by cos squared theta, so if you divided this by cos squared theta, and you divided this by cos squared theta, and you divided this by cos squared theta, you would actually get tan squared theta, because sine squared theta is, sine squared theta over cos squared theta is sine over cos, so it'd be tan squared theta, right? So you'd have tan squared theta plus cos squared theta over cos squared theta is 1 equals 1 over cos squared. Well, 1 over cos is secant squared theta, right? Or if you divided them all by sine squared theta, likewise, you would have 1 for dividing these 2 pieces, plus cos squared over sine squared would be cotangent squared, equals 1 over sine squared, which is cosecant squared. So these are all of your Pythagorean or Pythagorean identities, and they're all, of course, on your formula sheet. This picture, by the way, if you want to even like pause and just stare at it for a little while, all of these identities show up. Like, for instance, this one, tan squared theta, that would be this side, plus 1, or 1 squared if you wanted to think about it, is equal to your hypotenuse, which is secant squared, which is this part right here. In other words, what that's saying is tan of your angle theta spits out the distance on your circle to your nearest x-axis, whereas secant would express where your origin would connect to where your tan would connect with your x-axis. It's a big thing. You don't need to know it, but it is kind of cool that it's visual like that. Anyway, almost done here. Express as a single trigonometric ratio. Here we go. Secant x sine squared x minus secant x. Well, there's a couple ways we could go about this. Let's try the old-fashioned way where we say, you know what, change everything to sine and cos. Well, secant is a reciprocal of cos, so we'll say this is 1 over cos x times sine squared x. I think the writing's on the wall here. We might as well make it sine squared x over 1. I think we've seen that trick a couple times now, so I think we should be ready for it. Minus secant x, which is minus 1 over sine or cos x, right? How about let's write this now as one fraction on this side. See, I told you we were going with this. It's going to be sine squared x over cos x minus 1 over cos x. And hey, we got lucky on this one. They have the same denominator already. We don't have to do any tricks where we make one equal to the other. They already have the same denominator, so we can just subtract our numerators directly. We can say sine squared x minus 1 over cos x. Now this is where it's a bit of a stumbling block. This right here, sine squared x minus 1, is not directly on your formula sheet. But we do know that sine squared x plus cos squared x equals 1. Since this is an identity that is given to us, we are allowed to rearrange it. It's already proven. We don't have to worry about working just on one side or the other. We can rearrange this how we need. Let me say we could minus 1 on both sides and minus the cosine squared away. This is going to give me sine squared x minus 1 equals negative cosine squared x. I just minus this 1 and I minus the cosine squared. That's all I did. Now notice that we have this piece in our actual formula. This means we can replace it with what it was equal to. So we can change it to a negative cos squared x over cos x. This hopefully is a little bit more obvious now since we have cos squared on the top and a cos on the bottom. This becomes negative cosine x. Notice how it's just like a big game of like throwing in anything you know and working it through. Basically, if you start by changing everything into sine and cos, that's at least a good starting point. Then try to combine any fractions you have all together and just work from there. It's a bit of a process. It's something very different than what we're used to, but you get used to it as time goes on. Let's do another one here. Express as a single trigonometric ratio. I've chosen this one on purpose because it kind of breaks the old rule. Remember, the old rule is turn everything to sine and cosine first. It already is. And looking at this right now, there's not really anywhere obvious that we can go from it. There's a couple things you could try, but I wouldn't really go there, to be honest. But personally, the first thing I would go and try is breaking the rule and saying, you know what, I know sine squared x and cos squared x, sine over cos is tan. Since they're both squared, we can say this is actually equal to tan squared x plus 1. And wait a minute, if you look on your formula sheet, you can actually see that there's one on your formula sheet that says 1 plus tan squared theta equals secant squared theta. And hopefully you know that addition, order doesn't matter. 1 plus tan is the same thing as tan plus 1, right? Order doesn't matter there. So we could actually immediately change this to say, since this is the same as this, we can just replace that with secant squared x. And that was it. Look at that. That wasn't even like, that was like 2 steps. Not a big deal, right? But I chose this example on purpose because it does break that old rule. So again, like I said, you almost always will change it to sine and cosine first, but there are some rare occasions where it's actually easier to do something else. Here's another one, 1 plus cotangent squared x over secant squared x. You could try to change everything to sine and cos right off the bat, and I think you would actually be able to do it. You would have some success with it. But personally, the first thing I'm going to do here is I know 1 plus cotangent squared x is actually one of my identities. If we look on your formula sheet, you're going to see that 1 plus cotangent squared theta is actually equal to cosecant squared theta. So maybe what I'll try first, and again, it's just a game. I could be wrong when I do this. I'm going to change this to cosecant squared x over secant squared x. Cosecant over secant. Looking on my formula sheet, there's nothing I see on that one, but maybe now I can try to write this as sine and cosine. Maybe now it'll be a little easier to do that. Well, cosecant is a reciprocal of sine, so we could write this instead of cosecant squared x, we could write that as 1 over sine squared x over secant squared x is the reciprocal of cosine squared, right? So we could write that as 1 over cosine squared x. This is a fraction divided by a fraction. We don't like doing that, so we keep the first one. We change it from a divide to a times, and we flip the second one. Cosine squared x over 1. Multiply the top, multiply the bottom. You're going to have cosine squared x over sine squared x. Well, this hopefully is a little bit more familiar. Cosine over sine, if you look on your formula sheet right in the top right-hand corner, cosine over sine is actually equal to cotangent. Because they're both squared, we can say it's cotangent squared x. Whew! So that one was a lot beefier than the other one. We actually got through it though. Hopefully this is making sense. And again, if it isn't, please contact me. This stuff is brand new. So we're done. For practice, I want you to do page 296, questions 3 to 5 and 7 to 10. This is essential. Please make sure you're doing these questions. Please make sure you're checking your answers at the back of the book because this will be an essential skill for tomorrow's lesson where we're actually going to prove identities. And proving identities isn't much different than what we've done today. Anyway, as usual, reach out to me if you need any help. Best of luck.